Hello. In today's lesson, we are going to study about the introduction about the transition metal complexes and how are they formed and how to name them and what are ligands and what are their types. Okay. And in the last part of the lesson, we are going to study the stability of different types of ligands. Okay. So, students, you will be seeing in your book there are some compounds which are often given as written as this one, the one given on your screen. So, complexes actually these are the species which are formed when transition metal ion is bonded with ligands. Okay, so whenever you are writing a complex, we have to use a square bracket. Okay. So inside the complex there is a transition metal ion, the one which I am using this pink color. You can see copper is a transition metal ion, and the one with green color, these two are the ligands. Okay, so ammonia is a ligand and water is a ligand in this complex, and they are bonded with a dative covalent bond with the empty orbitals of the central metal ion. Okay, so this thing is called complex. Next, we have to know what are ligands. Okay, so basically ligands are electron pair donor species which are forming dative covalent bond with the empty orbitals of the central transition metal ion. As you will be knowing, the dative covalent bond, the shared pair of electron comes from the same atom. So when you are talking about complexes, so inside the complexes, the ligands are forming dative covalent bond with the empty orbitals of the central transition metal ion. Okay. So as regarding the charge on the ligand, ligands can be neutral like H2O, NH3, ammonia is a ligand, or even sometimes carbon monoxide also can act as a ligand in some of the complexes. Okay, carbon monoxide also a ligand. So these are the neutral ligand, and some of the ligands are negatively charged, like you can see cyanidine, it's also called cyanoligand, and hydroxidine, which is also a negatively charged ligand. Okay, so basically the ligand main purpose is to have a lone pair of electron, at least one lone pair of electron, which should be able to form a dative covalent bond with the empty orbitals. Okay, I have shown you one complex over here. So this is a complex of iron 2 plus with cyanidine or cyanoligand. You can see there are 6 cyanidine bonded with dative covalent bond, and as you will be knowing, dative covalent bond is represented by a arrow. Okay, this arrow represents the lone pair of electron from cyanidine. So cyanide ion is donating the pair of electron to the empty orbitals of the Fe2 plus. So, and the shape of this complex is octahedral, because as you will be knowing, when a central atom is surrounded by 6 electron pairs, so the 6 electron pair have to be arranged according to the valence shell electron pair repulsion theory. They have to be arranged at in order to maximize distance and the minimize repulsion. So the best shape for the 6 coordination number 6, or the central atom ion is surrounded by 6 ligands, it will be octahedral. Okay, the IUPAC name of this complex you can see over there, hexacyano ferrate 2. Okay, and the detailed naming we are going to do in the later part of the lesson. Next, we have to know, some of you will be wondering how the transition metal ions are able to form dative covalent bond, because dative covalent bond usually they are associated with non-metals. Okay, so if you look at this one, this example will make you understand how the formation of dative covalent bond takes place. So inside this complex we are having copper 2 plus ion which are bonded with 4 ammonia ligand or amine ligands. So you can see ammonia is having a lone pair of electron, right? So for copper 2 plus, it's 3d9. The electronic configuration you can see it's for the copper atom. Okay, the first one is for copper atom. So copper atom is having atomic number of 29. So the electronic configuration is going to be 4s1 and 3d10. For copper 2 plus, it will be 3d9, because we have to remove one electron from 4s and one of the electron from the 3d orbital. So they will be like it will be 3d9, right? So it's going to be, there should be one electron over here, right? But if you, as you can see from the diagram, this electron is not drawn there. Okay, so when complex is being formed, this electron is going to be promoted from 3d this orbital to the 4p, there is empty orbital. Now question arises why it's doing like that. Okay, so it has to do with the geometry of the complexes. Please remember, when the coordination number of a complex, I told you already, the coordination number is the number of dative covalent bond made by the central metal line. So over here the coordination number is 4, right, for this complex. So whenever there are 4 ligands, usually it will be going for square planar geometry. Okay, you will be knowing the square planar geometry. The central atom is surrounded by 4 electron pair. For having this geometry or square planar geometry, we need to have the hybridization. You have studied even in organic chemistry. So the hybridization which is there for square planar complexes, it has to be dsp2. So it means you need to have one d orbital to be used for the formation of dative covalent bond, and one s orbital and 2 of the p orbital. Okay, so that's why the hybridization is said to be dsp2 hybridization. You can see when you are transferring this electron from the d orbital to the 4p orbital, so this orbital of one of the d orbital gets vacant. Okay, so now this orbital can be used to form a dative covalent bond. So as you can see in the last diagram, one of the d orbital is used for making dative covalent bond, one s orbital and 2 of the p orbital. So the hybridization for this complex is going to be dsp2 hybridization, and whenever we have dsp2 hybridization in a complex, the shape of the complex is going to be square planar. Okay, now I can go for next. Some of you will be wondering, like the complex, there is one complex given in your textbook for A level. The complex is CuCl4 minus 2. It's given in your textbook. You would have seen this complex is going not for square planar shape, this is going for tetrahedral shape. Okay, now the question arises why this copper complex with 4 chloro ligand is going for tetrahedral shape, while the NH3 complex, the complex with NH3 is going for a square planar shape. Please have a look at this one. For copper 2 plus, when there are 4 chloro ligand, as you will be knowing, chloro ligand are highly electronegative ligand. So for these ligands, actually what is happening, the electronic configuration will be 3d9, like I told you for that one, the above one. But this electron, you can see the electron in the last orbit, we are not going to promote. Like this electron has to be kept in the same orbital. Okay, so the reason for this is because as you will be knowing, chlorine is one of the most electronegative element among all the elements. So when chloro ligands are there, so there will be greater repulsion between the ligands. So in that case, you will be going for tetrahedral shape. Okay, so the shape of the complex is going to be tetrahedral. So when the complex is having tetrahedral shape, the bond angle is going to be 109.5, while for square planar the bond angle is going to be you will be knowing it's 90 degree. So when there is a chloro ligand, because it's having greater repulsion between the ligands, so it will be opting for tetrahedral shape because it will have a greater separation between the ligands, right? So please remember, whenever there are 4 chloro ligand, and you cannot have more than 4 chloro ligand inside the complex because of the same reason, because they are highly electronegative. So you can't have 6 chloro ligand. So whenever chloro ligand is inside the complex, there will be 4 chloro ligand, and the shape of the complex is going to be tetrahedral. I can give you one more example. There is another complex having chromium. So you can see this one, CrCl4, and the charge on this one will be -1, right? Because chromium is mostly 3 plus and chloro ligands are -1 for each one. So the overall charge of the complex is going to be -1. So this complex also goes for tetrahedral shape. And I can get you one more example for square planar complexes. So nickel complex with 2 ammonia ligands and 2 cyanide ligands. So this complex also will be going for square planar shape. So to summarize what I can say, if a complex is having 4 chloroligand, all of these complexes will be going for tetrahedral shape, because the hybridization will be sp3 hybridization, and sp3 hybridization, the shape of the complex is going to be a tetrahedral, while other ligands, other complexes which are having 4 ligands and they are not chloroligand or they are not electronegative ligand, so then the shape of the complex is going to be square planar. Okay. Now let's move on to the, I hope it's very clear. So after this one, now let's move on to the next topic. As you will be knowing, there are rules for naming organic compounds. Similarly, they have the IUPAC committee have given rules for naming the complexes. So there are 3 or 4 rules, and whenever you are naming complexes, we have to make use of these rules. Okay. So the first rule is ligands. Whenever you are naming a complex, ligands have to be named before the metal line, and the number of ligands should be indicated by prefixes. For example, there are 2 ligands, we have to be using the prefix di. If there are 3 ligands, we have to use the prefix tri, and for 4 we have to use the word tetra, and for if there are 6 ligands, so we have to use the prefix hexa. And the ligand name will be proceeding before the metal name. Okay. So the ligand, if the ligands are negatively charged, the ligand name should end in O, right? For example, cyanidine, in inorganic chemistry we say cyanidine, but when it's a ligand in the complexes, it won't be, we will not be calling it cyanidine. In the complexes we have to say this as cyano. Right. So, and similarly, you will be knowing hydroxidine. So this is a hydroxidine, but as a ligand we cannot say hydroxide. We have to say this ligand as hydroxo. Please remember it. Okay. So any ligand which is having a negative overall charge, that the name should end in the letter O. So you can see there are common ligands given for you in this list, and you can see when, the ligands which are negatively charged, all of them, their name ends in O. Like you can see it's hydroxo, and for this oxide it will be called oxo. Cyanide is going to be said cyano, and you can see the even carbonate ion can as a ligand will be called carbonato, and you can see the last one which is given over here, nitrite ion, as a ligand will be called as nitrato. Alright, we have to remember this one. And other names are given for you. Water as a ligand will be called aqua, and NH3, we say amine, but as a ligand it has to be said amine with double M. Okay, take care of this. And carbon monoxide as a ligand has to be said carboxy. You will be knowing the last one which is given for you. This actually we use this abbreviation in the complexes is called EN. The full form of EN is ethylene diamine, or you can say diaminoethane. Okay, so these ligand names we have to know them. So after writing the name of the ligand and the number of ligand, we have to write the name of the transition metal. And after writing the name of the transition metal, its oxidation number has to be written in Roman numerals. Now let me take one example for you before going to the last rule. Okay. So after, let us name this complex. Okay. So Ag with 2 NH3. And there is +1 on the top. So as you can see, there are 2 ammonia ligand present in this complex. So we have to, because there are 2 ligands, we have to say di, because there are 2 ligands, and NH3 as a ligand is called amine. So the name of this complex is going to be diamine, and Ag is standing for silver, so silver, and the oxidation number of this complex is +1. And as you will be knowing, ammonia is a neutral ligand, so whatever charge is given on the top of the complex, that is due to silver. So silver oxidation number is 1, and that we have to write in Roman numeral, and this is ion. So you can see there are 2 ammonia ligands, so we have to say diamine, silver 1 ion. Okay, right? So now let me take one more example for you. For example, if I'm having Fe H2O6, and there is +3 on the top. So this complex is going to be said because there are 6 water ligands. So we have to say hexa aqua iron, and the oxidation number of iron over here is +3, so I have to say iron 3 ion. So this complex ion will be said hexa aqua iron 3 ion. So we have to always remember, whenever you are naming a complex, we have to say the name of ligand first and then followed by the metal name, and the number of ligands should be indicated by prefixes like di, and for this one we are using hexa. Now let's move to the next. The last rule which I have given for you in red color, please remember this one. When the total metal transition metal complex ion is having a positive charge or neutral charge, we have to use the normal English name for the metal, okay, like iron or silver. But when the complex ion is having overall negative charge, so we have to use Latin name. You will be knowing there are some metals with the Latin name. I have written for you these metals which are having Latin name, and you will be knowing their symbols are different their English name. So for gold, the symbol for gold you will be knowing it's AU, because the Latin name of gold is aurum, and for copper it's Cu, and the Latin name of copper is cuprum, and for iron the Latin name is ferrum, so its symbol in the periodic table is Fe, and for silver it's argentum, and the Latin name of the symbol for silver is Ag, right? So these 4 are the common metals whose Latin names are there, and we have to apply them, okay, when you are naming the complexes. And last rule is saying, if there are multiple ligands present in the complex, like we studied before, there were a complex having multiple ligands like this one. You can see it's having ammonia ligand and cyanide or cyano ligand. So when there are multiple ligands present in the complex, we have to name them in alphabetic order, right? So this is cyano ligand and this one is amine ligands. So first of all we have to name amine, and then we have to say cyano, right? Okay. So now let me do some example for you, and then I have more example which we'll be doing together. Okay, so please have a look at this one. So we have to use the Latin name when the complex ion is having a total of negative charge. We have to use Latin name, and if Latin name is not there, like for some metal Latin name doesn't exist, like for chromium. And so if there is a complex having chromium and having a negative charge, we have to say chromate. And if there is a complex having manganese, so manganese will be said manganate. You will be knowing, so there are some common ion, like you will be knowing Cr2O7-2 is called dichromate ion. This is a complex ion, and this is called dichromate 6 ion, because the oxidation number of chromium over here is +6. And you will be knowing there is a complex ion MnO4-1. So the name of this ion, complex ion, is manganate. Okay, and manganate, and the oxidation number of this manganese is +7, so it's called manganate 7 ion. So we have to just remember one thing, when the complex is having a negative charge, you have to use Latin name if it is available. If Latin name is not there, then English name. But basic thing is that the name of the metal should end in 8, okay? Like chromate, dichromate, manganate, and iron. If it is a negatively charged complex, we have to use ferrate. Right. So now we have to apply these rules, and we will try to name few of the complexes. I have written 6 or 7 complexes for you. Now let's go to the naming of them. So look at the first complex, the given on the left side. So if you want to name this complex, you can see there are 2 different ligands present inside this complex. There is water ligand, and now we have even OH ligand. Water is called aqua, and OH minus ions are called hydroxo. So if there are multiple ligands present, we have to follow the alphabetic order. So we have to say first aqua, then we have to say hydroxo. And there are 3 water ligands present. So the name of this complex is going to be triaqua, then trihydroxo, And you can see this complex overall is having no charge, so we have to use normal English name of the metal. So triaqua trihydroxo iron, and the oxidation number of this iron is +3. So because there are 3 hydroxide ions and overall charge is 0, so it means the iron over here is 3 plus. Okay, so the full name of this complex is going to be triaqua trihydroxo iron 3. Now look at the second one. In the second complex, you can see there are 4 chloro ligands. So we have to say tetrachloro. Cl ligand is called chloro. So the name of this complex is going to be tetrachloro. This time we will not use the word iron, because I told you in the last rule, if the complex is having a negatively charged complex, if it is a negatively charged complex, we have to use the Latin name. And Latin name of iron is ferrum. And the ending will be in the letters 8. Okay, so the name of this complex is going to be tetrachloroferrate, because we have to use the Latin name, and oxidation of this iron is +2. So you have to say ferrate 2 ion. Again, I will say how will you work out the oxidation number, because chloro ligands are -1 and 4 of them are there, and iron is +2. So when iron is +2, +2 -4, overall charge is going to be -2, right? Now look at the third one. The name of this complex, again there are 4 chloro ligands, so you have to say tetrachloro. Now platinum is not having English Latin name, so you have to use normal English name, but end in 8. Okay, so the name of this complex is going to be tetrachloro platinate. Don't say platinum, it will become platinate, and the oxidation of this platinum is +2. So you have to say tetrachloro platinate 2 ion. If you look at the fourth one, now here there are 6 water as a ligand. So as you will be knowing, water as a ligand is called aqua. So 6 of them are there. So the name of this complex is going to be hexaaqua. CO is standing for cobalt, hexaaqua cobalt, and the overall charge is +2. So cobalt 2 ion. And as you can see, water is a neutral ligand, so whatever charge is on the complex, that is due to cobalt. So the oxidation number of cobalt is +2. Please look at the sixth one. Fifth one is having cyanone ligand and NH3 ligand. NH3 is called amine, and Cn- is called cyano. So first of all, we have to name amine. So there are 2 of them. So we have to say diamine and dicyano, and we have to use nickel because it's a neutral complex. Okay, so nickel, and the oxidation number is going to be +2. As you will be knowing, cyanide is -1, so there are 2 of them, so -2, and for nickel is going to be +2. The last complex which is given for you is VO2, and the overall charge is +1. When oxygen is a ligand, it's going to be, we have to say oxo, and there are 2 oxide ion present as a ligand, so the name of this complex is going to be dioxo vanadium, and the oxidation number of this vanadium is +5. And how you know? Because there are 2 oxide ions, and as you will be knowing, oxide ion, each one is -2, so 2 oxide ion -4, so 1 vanadium is going to be +5, because overall charge is +1. So it's going to be dioxo vanadium 5 ion. Alright, okay, so by applying these rules, we have to name the complexes, and if there are multiple ligands present in a complex, we have to follow the alphabetic order, like this one and this one, right? Okay, now let's move on to the next topic. In this part of the lesson, we are going to study different types of the ligands. So ligands can be broadly divided into 3 categories mainly. So the first category is called monodentate ligands. As you can see from the definition, monodentate ligands, these are the ligands which can form only one dative bond with a central metal ion, right? And most of the ligands whichever we have studied till now, most of the ligands are monodentate ligand. I told you before, water or aqua ligand, chloro ligand, hydroxide ligand, NH3 and oxide ligand, all of them can form just one dative bond, and when they can form one dative bond they are called monodentate ligand. Okay, and one of the example is given for you with iron 2 plus with cyanide ligand. But take care of only whenever you are drawing the complex diagram, please take care cyanide ion, because many students lose this mark. Cyanide ion is having pair of electron both on nitrogen. Nitrogen is having a lone pair when you are drawing dot and cross, and carbon is also having one extra electron. Due to that extra electron is -1. So whenever you are starting the arrow, you have to start arrow from not from nitrogen, you have to start the arrow from carbon side. Many students, they do mistake because they may think because nitrogen is also having a lone pair of electron, so they may start from this lone pair of electron. Okay, I can use this blue color. So never start, because the dative bond is can also be formed by nitrogen, but you have to, whenever you make cyanide ion in the complex, you have to start arrow from carbon side, not from hydrogen side. As you can see on the left, this cyanide ion. So please, I mean to say, never show it this way. Cyanide ion can not connect. The cyanide ion should connect from carbon side, so you have to show it this way. Okay, this way. Okay, and never start arrow from the other way, like from nitrogen side. It's wrong. Okay, so whenever cyanide ion is a ligand, you have to make sure you are connecting from carbon side, not from that nitrogen side. Okay, next ligands are said to be bidentate ligands. You can understand from the word itself, the word bi mean two. So the ligand which are able to form two dative covalent bond, because these ligands are going to have two atoms which can donate two electron pairs to form two dative covalent bond. The two examples which are very common are En. I told you already, this is an abbreviation. The full name of this En is 1,2-diaminoethane. Because it's an organic ligand, so the name will be 1,2-diaminoethane, and the short form in the complexes we are usually using this abbreviation. It's called En. And for ethane diiodine, the ligand name is called oxalate. In organic chemistry, we are saying this ligand as ethane diiodine. And it can form, two dative bond. One it can form from this side, from this oxygen, and this one can even form from this oxygen. Similarly, this although ligand can form two dative bond, one from this nitrogen and one from this nitrogen. In some of the paper, they are asking you how these ligands are able to form two dative bonds. So you can say, because they are having two electron pair donor atoms which can form two dative bond with a central metal ion. And last type of the ligands are called polydentate ligands. So these are the ligands which can form minimum of two or more than two dative covalent bonds. So any ligand which is able to form multiple dative covalent bond with the central metal ion, they are said to be polydentate ligand. In our syllabus of A levels, we are having only one of the ligand, which is polydentate ligand, which is called EDTA. Again, it's an abbreviation, like En is an abbreviation. So similarly, EDTA is also an abbreviation. So actually, EDTA is a derivative of this compound, like En. It's a derivative of En. Now let me draw the structure of EDTA, because I saw in some of the past paper they are asking you to draw the full structure of EDTA. And you can see the full name of EDTA is ethylene diamine, and you can see its name is quite similar to this, right? So this is ethylene diamine. But you can see only the last two words are different. Okay, so the name of EDTA is ethylene diamine tetraacetate. So actually, why it's called acetate? You will be knowing acetic acid is actually ethanoic acid. In older books they were calling it as acetic acid. Now we say ethanoic acid, the IUPAC name, but in old books it was said to be the common name of ethanoic acid is acetic acid. And when you remove one proton from there, it becomes CH3 COO minus with a pair of electron. This is called acetate ion. Now you can see the name of this one. It means actually there are 4 hydrogen with the 2 nitrogen atoms. You can see 2 on this side and 2 on this side. So if you are replacing all these 4 hydrogen with acetate ion, then the compound will, or the ion will be called tetraacetate. So now let me draw the structure for you, because in some exam they ask you to draw the structure of EDTA. So you will have CH2, CH2. Please have a look at the structure of ethylene diamine, or EN, because it's basically derived from there only. Okay, so you will be drawing nitrogen on this side, 1 nitrogen on this side. So you can see each of the hydrogen atom is replaced by acetate ion. So it's CH2 COO minus, CH2 COO minus, CH2 COO minus, and even on this side CH2 CH2 COO minus with a pair of electron. And you can see, and nitrogen is having 1 lone pair for this nitrogen and 1 from this nitrogen. So in total it can make 6 dative bond. You can see it can make from even from the lone pair of nitrogen. So in total EDTA ligand, which is having a charge of -4, and that charge you can work out because each acetate ion is having a charge of -1. So in total it will be a charge of -4. You can understand from here, -1 here, -1 here. So total there are 4 minus charges. So EDTA overall charge is -4. And how many dative bond it can form? It can form 6 dative bond. So please remember, whenever EDTA is used in a complex, there will be only 1 EDTA ion, because 1 EDTA ion can form 6 dative bond, right? I hope this is very clear. So let's move on to the last topic for today. So last topic is regarding the stability of the ligands. Actually, stability of the ligand depends on the type of the ligand. As I said, there are 3 types of ligand. We call them monodentate ligand, bidentate ligand, and polydentate ligands. So please remember, bidentate ligand form more stable complexes than monodentate ligand. And what does it mean? You remember, in displacement reaction, a more reactive element can displace less reactive element. So if a ligand is able to form stronger bonds, or it will be able to make the number of particles increase, because actually the reason behind this is, when a bidentate ligand is replacing a monodentate ligand, there is an increase in entropy. As you will be knowing, natural or spontaneous processes are accompanied by increase in entropy, right? So when a bidentate ligand is replacing a monodentate ligand, there is increase in the number of particles. Now let me give you an example which will make you understand this. So what I will do, I will take a complex. For example, I'm taking nickel complex with OH ion, 2 OH ion, and 4 water. So please remember, in total we should have 6 dative bond formed by the central metal ion. So nickel is having 2 OH ion as a ligand and 4 water. Okay, in total it will be 6. So the state, because a neutral complex, I told you in the last lesson, it will be solid, the state symbol, and I will be taking only 1 EDTA. First, let me take bidentate ligand, because EDTA is polydentate. So I will be taking 3 EN. In equation, usually we use the abbreviation only. Okay, EN mean ethylene diamine, this one. So this ligand can form 2 dative bond. So because we want to make total of 6 dative bond, so one EN molecule can make 2 dative bond. So it means we have to take 3 EN, because 1 is going to form 2 bonds, so 3 will be making 6. So what will happen? This EN ligand will replace the ligand inside the complex. So the product you will get this. So nickel En3, and as En is a neutral ligand, so the charge of the complex is going to change. Before it was 0 or neutral. Now this complex will be +2. So now this one, the physical change will be there. The solid precipitate will become an aqueous solution, okay? And the ligand which were inside the complex, now they will be removed. So the 2OH ion will leave the complex, and 4 water, 4H2O. The state symbol water, you have to put liquid. And for En, we can use the state symbol aqueous, because an aqueous. All right. So now, if you please have a look at the wording, when a bidental ligand is going to replace a monodental ligand, there is a change in number of particles. How can I explain you? Look at the number of particles on the left side of the equation. You can see there are 3 En ligand, and this complex is considered as 1 particle. So total number of particles on the left side are 4. Please look at the right side. On the right side, you can see there is 1 complex ion, there are 2 OH ion and 4 H2O. So the total number of particles on the right side of the equation are 7, right? So when the forward reaction takes place, there is an increase in number of particles from 4 to 7. So when the number of particles increase, obviously there will be greater randomness of particles, so there will be increase in entropy. So the entropy change, or delta S, will be positive, right? And any reaction which is involving increase in entropy, that will be spontaneous. Spontaneous means the reaction will go on without any external help, okay? It will be spontaneous, right? So that's due to this reason, or due to increase in entropy, a bidental ligand can replace any monodental ligand. Okay, now let me take another example for this before we move on to the last part. This time what I am going to do, I will take another complex. Let's say I am taking this time a zinc complex with 6 NH3 plus 2. This time I will take ethane diovate ion. You will be remembering the formula of the ion is C2O4 minus 2. Again, I have to take 3 of the ligands, because of the same reason, because one bidentate can form 2 dead bonds, so we have to always take 3 bidentate ligand. So these ethane diode ions are going to replace all the amine ligands. So the complex we will be getting will be like that. Please look at the charge, okay? There will be change in the total or overall charge of the complex. So Zn, C2O4, there are 3 of them. Now the total charge of the complex is going to be, because each ligand is minus 2 and 3 are there, so minus 6, and Zn is plus 2, so overall charge is going to be minus 4, and the state symbol will be aqueous, and the ammonia ligand or amine ligands are going to go outside the complex. 6 NH3. Again, if you look at the number of particles on the left side of the equation, there are 4 particles, and on the right side of the equation there are 7 particles. Right, so forward reaction is again leading to greater increase in number of particles, so entropy is increasing. Therefore, because of this reason, this reaction is spontaneous, right? I hope it's very clear. So now let's go for polydental ligand. As you will be knowing, polydental ligand, I told you EDTA is one of the most common polydental ligand, the one which we have just discussed previously. So I told you over there, when EDTA is replacing monodentate or bidental ligand, basically the reason is same, because one polydental ligand can form 6 dead bonds. So when one EDTA ligand will be replacing a monodentate or bidentate ligand, there will be increase in number of particles. So there will be increase in entropy. So because of this reason, a polydentate ligand can replace or displace any monodentate or bidentate ligand from its complexes. Let me take 2 examples for you. Have a look at this example. This time I'm going to take chromium complex. So Cr, OH4, H2O2. The overall charge on this one is -1. Aqueous. This time I'm going to take EDTA. And overall charge on EDTA is -4. So one EDTA is only required. So whenever you are writing ligand exchange reactions for EDTA, you have to use only one EDTA. right? So EDTA is going to replace all the ligand which are inside. So it's going to be Cr EDTA, and the overall charge is of this complex is going to be -4 for EDTA, and chromium over here is +3, so overall charge will be -1. Okay, you have to take care of the overall charge. It will stay unchanged because 4 hydroxide ions were also -4, so the charge doesn't change. It's AQ, and the ligand which were inside, now they will be removed. So 4OH minus and 2H2O. And as you can see, because on the left side there are 2 particles, and on the right side of the equation there are 7 particles. You can see the polydentate ligand or EDTA is causing a much greater increase in entropy, right? So because of this reason, that's why polydentate ligands are even more stable than monodentate ligand, because they cause greater randomness of the system, and then the reaction is spontaneous. Now let me take last example for you. In this one I will be using let's say copper example. Okay, copper complex which should be having a bidentate ligand. So I'm using copper, C2O4, 3 of the ligands, and the charge on this one, you will be knowing copper is mostly +2, and ethane diode ions are -2, 3 of them are there, so -6 +2, overall charge will be -4, aqueous. And I have to take 1 EDTA, which is -4. So EDTA is going to replace all the ethane diode ions, so the complex which we will get will be like this. So copper with EDTA, and overall charge will be now -2. Please take care, okay, because EDTA is -4 and copper is 2+, so overall charge will change. It will become -2 plus 3 ethane diode ions are going to move outside the complex. So these are 3 C2O4 -2 ions which will go outside the complex. Again, there is a change in number of particles, but this change is not greater than the above one. So over here you can see we are having 2 particles on this side, and on the right side of the equation you can see the 2 particles are changing into 4 particles, right? So again there is an increase in entropy there. Because of this reason, the polydentate ligand like EDTA can displace even monodentate ligand or bidentate ligand also, and these reactions are said to be ligand exchange, as we already said before also. Okay, so students, with this topic we are going to end the lesson for today. I hope everything is clear about today's lesson, and if there are any suggestions or any comments, you are most welcome to send me comments in the comment section, and please like and subscribe to my channel, and because then we can upload more videos which are regarding for your A-level chemistry, which will help you to understand chemistry in a better way. Thank you so much. Thank you. Bye bye.